Salut, comment ça va mes amis? That's French for hello, how are you doing friends? I'm sure you're doing great, but you will do even better once you solve this problem that I'm going to explain you right now. The feeling, the satisfaction. I know sometimes you doubt yourself, you're like, all those people working for Google and Facebook and Amazon and Twitter and whatever. How can I be like them? How can I achieve this? You doubt yourself, and I was where you are at right now. I had my doubts. Then I started elementary school, things got better. But still, sometimes this feeling can be a bit crushing. So let's pick ourselves from the dust, clean ourselves, free our hands, stretch them, stretch the fingers, and let's jump onto Leetcode.com, try to solve a problem together. 1712. Ways to split array into 3 subarrays. A split of an integer array is good if the array is split into 3 non-empty contiguous subarrays, left, mid, and right, respectively from left to right. The sum of the elements in left is less than or equal to the sum of the elements in mid, and the sum of the elements in mid is less than or equal to the sum of the elements in right. Meaning the first is the smallest, the middle is the middle, and the last one, the right one, is the largest. Given nums, an array of non-negative integers, return the number of good ways to split nums. As the number may be too large, return it modulo 10 to the 9th plus 7. And we have had a similar problem before where we had to apply modulo operation so that we don't have an overflow of our result. The logic here is as follows. You solve the problem as if there was no overflow issue, and then you apply the modulo operation to any place in your code where you believe the operation can result in an overflow. Let's now think of what the brute force solution for this problem would look like. You have an array split in 3. That means you have indices I and j at the split points of this array. And if you go through all possible i's that split your first array from the rest, and you go through all possible j's that split your last array from the rest, you will eventually have exhausted all your options. And so in quadratic time, you can generate all possible splits and verify if they are preserving the invariant that the first array needs to be smaller than the middle, which needs to be smaller than the last one, subarrays. With the help of prefix sums, we can answer the question of whether one subarray is smaller than the next one in constant time. So we should definitely do that. Still, that solution would be quadratic because all possible I and j pairs are n squared, where n is the length of the array. The number of the elements in the array is 10 to the 5th. So unfortunately, quadratic doesn't work for us. How can we do better than quadratic? Meaning, how can we do, let's say, n log n, an obvious candidate? Well, the idea that you need to do n log n should force your thought towards binary search solution. And in fact, yes, there is a binary search solution. The idea is for every left subarray, you have a certain index at which the middle subarray becomes large enough to be larger than the leftmost subarray. So for a given I, you can iterate after this I and find an index j at which that array, that second array, becomes large enough to satisfy the condition. You can, in exactly the same way, find even further towards the end another index k at which that second array stops being smaller than your right subarray. In other words, there is an interval between j and k in which your middle subarray is just about right. It is bigger than your left subarray and it's smaller than your right subarray. And for any index between j and k, that condition would be true. Once you pass k, that second subarray will be too big, won't satisfy the condition that it needs to be smaller than the rightmost subarray. And for any index before j, the middle subarray will be too small, therefore not satisfying the first condition to be larger than the first subarray. And now the question becomes, for a given I where we have split our first array, what is the range, what is the interval, what are the corners of that interval in which we can pick end of the second subarray and it will satisfy both of the conditions, meaning being the middle subarray. That can be done with a couple of binary searches, one for the beginning of the interval and one for the end of the interval. Alright, how does the binary search solution look like? First, we'll calculate all of our prefix sums. And that's very standard. If you are not familiar with prefix sum calculations, I encourage you to look for a problem discussing just this. But what we do here very shortly is we will calculate for every element what's the sum of all elements up to and including that element. So for the first element, that will be just the first element. For the second element, the prefix sum at index 1 would be the sum of 0 and 1 elements. For prefix sum 2 will be the sum of 0 plus 1 plus 2. And there is a very simple linear way to do that. Prefix sum for I equals to the prefix sum of I minus 1 plus the current element nums I. After we have calculated our prefix sums, we'll iterate through all possible first subarrays, I being the beginning of our second subarray. And for every one of those, we'll count the number of possible splits, the number of possible end indices for our second subarray. That requires a couple of binary searches here. We find a range in which we could pick the second split point. And because all of the positions within that range are valid, this is actually the number of valid splits that we can add to our result. So we go through all possible first splits, and for them we find the ranges of possible second splits. We add that to the total and we return it. So that's the binary search solution. I won't go into detail of how the binary search is implemented. That's the solution I went with. That's what I implemented during the competition last Saturday. However, there is a better solution. There is a linear solution, and it looks like so. And here's the idea about it. We have the binary search solution, right? For every I indexed as a first split of the array, we would have a range for the second split. When this first array gets larger, when I shifts to the right, what happens with our range for our second array? If you think about it, the second array can never become smaller, right? We're only working with positive numbers, which means the beginning of that range can also only shift forward. The end of that range can also only shift forward. If all the three indices can only shift forward, that means they can go from 0 to n only once, which means our solution will become linear. Right? In the previous case, we had for every I log n because of the binary search here. Now, even though we have three indices, we actually don't have them jumping back in any scenario. They only progress forward. So that gives us linear time. You will see in the solution two loops here, but if you reason about it, it's linear. Armed with this amazing insight, first, we calculate again the prefix sums. And this time we've used the same array. We've overwritten the initial values with the prefix sums just because we don't really need the original values. We could have done that in our previous solution as well.
What about aubergine as in purple?
Then we'll iterate over all possible first split points where our left array finishes. And for all of those, we'll find two things, j and k, the beginning and the end of our second array's split point range. Meaning, what's the minimum index at which we can put the second split point, and what's the maximum index at which we can put the second split point. This is the condition for which we'll check. This statement is a bit convoluted, nums j less than 2 times nums I, but what it means really is the second subarray is smaller than the first one. Remember, nums j and nums I are right now prefix sums. The moment this is not anymore true, then we found our j. That's where we can start putting the split point between the middle and the right subarray. We'll do the same or similar calculation for k. We'll try to find the position at which k preserves the invariant having the last subarray nums n minus 1 minus nums k, that's the sum of the last rightmost subarray, is more than or equal to nums k minus nums I. As long as this is true, we'll keep iterating k. When that stops being true, that's where the end of our valid range is. Once we have identified the beginning and the end of the valid range, we'll do what we've done in our previous solution. We'll add the difference, we'll add the number of possible positions for our second split to the final result, because this is all the possible splits of the array in 3 for that I. Next, we'll move to the next I and we'll again find the range. The only difference between the previous solution and this one is now we know that our j and k only will progress forward from where they have been until now. So we won't have to binary search, we won't have to brute force search the whole interval. It will be just forward iteration and it will guarantee us linear time. At the end, we'll return the result and we're done. Good job! Well done! Fantastic! You guys made it again up to here, and that probably defines your future as stellar. We solved the solution. We solved the problem.
We found the solution.
And we're done! We nailed it. We solved the problem, or read the solution somewhere and explained it after. This problem has been asked by Robinhood, so if you wanna enter the brokerage space. By the way, the founder of Robinhood is a Bulgarian guy. Is that random? Is that a happenstance? I don't think so. Keep coding, keep solving problems. Be like Robinhood, take from the rich, give to the poor. Hopefully that will get you on the right path. But if it doesn't, then comment below, let me know about it. I'm curious to find what can take you astray from the path you've chosen. Until next time, see ya!